So, we were discussing about this 3 op amp instrumentation amplifier in the last class, and we had gone to the extent of finding out what the common mode gain is from this point to this point and what the differential mode gain is from this point to this point. Common mode gain here, common mode voltage here at the input is V A plus V B by 2, that is the common mode voltage at the input of these two amplifier stage. At the output again V C E I, V C O here is again this also equal to V A plus V B by 2, because these two get cancelled. So, the common mode voltage remains same, gain is 1. By introducing this stage, as far as the common mode voltage is concerned, the gain is just remaining 1. The common mode input is V A plus V B by 2, here also it is V A plus V B by 2. But as far as differential mode is concerned, here it is V A minus V B at the input, and here it is V A minus V B plus V A minus V B into 2 R B by 2 R E. These two will get added when you subtract. So, this is equal to V A minus V B into 1 plus R B by R A. So, you can see that this stage, introduction of this stage of 2 amplifier has resulted in no change in common mode gain, but an increase in common mode differential mode gain of 1 plus R B by R A. So, R B by R A can be arbitrarily made high, so as to make the differential mode gain very high. And as far as this stage is concerned, we know that the differential mode gain is 1, because R is chosen, and common mode gain depends upon how best these are matched. So, if the tolerance is delta, that is the tolerance, then we know that the common mode gain from here to here is going to be 2 delta, and in effect the differential mode gain of the overall stage is V A minus V B into 1 plus R B by R A, and common mode gain is 2 delta, and therefore, common mode rejection ratio is 1 plus R B by R A divided by 2 delta. So, this circuit is one of the most popular circuits. It is available as an integrated circuit itself, wherein 2 terminals have been brought out here, so that this can be made variable if you want, so as to vary the differential mode gain, and you can design it for any differential mode gain that you want. So, this circuit is one of the instrumentation amplifier setups. Now, another instrumentation amplifier which uses only 2 amplifiers, 1 and 2, is shown here. V A is applied here, V B is applied here, and therefore, this voltage is V A and this voltage is V B. So, since this is V A and this is V B, the current in this is V A minus V B by R F. The current in this is V A by R. So, the total current in this is going to be this current plus this current, which is V A by R plus V A minus V B by R F, that is the total current in this. So, V naught prime here is going to be V A plus the voltage drop across this, which is this current into R, which is V A plus V A, that is 2 V A plus R by R F into V A minus V B, that is the voltage at V naught prime. This is V B. This current that is coming is V A minus V B by R F. So, because of this current here, this current plus this current is going to pass through this in this manner, and therefore, the voltage across this is going to be what is going to be subtracted from VB. So, V naught is equal to VB minus one current will take VA minus VB by RF, that into R. So, minus VA minus VB into R by RF, that is this part of the current going through this and generating voltage. Then this current which is twice VA minus VB by R into R. So, twice VA minus VB, one potential, okay, and R by RF VA minus VB divided by R multiplied by R. So, that minus VA minus VB R by RF. So, essentially we will see that V naught is going to be equal to this VB twice VB minus twice VA, twice VB minus twice VA, like this, okay. Then plus VA minus VB into R by RF, VA minus VB R by RF, which is plus VB minus VA into R by RF 2 times. VB minus VA, okay. So, I can make this plus VB, this is plus VB minus VA, this can be plus. So, it is VB minus VA by RF into R twice that. So, essentially again gain is, okay, 2 times VB minus VA, okay, into 1 plus R over R. So, once again we see that this is going to act as a differential amplifier, but uses only 2 op amps, and buffering action is still there because these are the non-inverting terminals here to which inputs are fed. Okay. So, these 2 instrumentation amplifier configurations are quite popularly used in practice. We had discussed how to multiply a voltage by a constant so far, that is amplifiers. Then we have also discussed how we can add voltages and then subtract voltages in the instrumentation amplifier. The other mathematical operations are linear mathematical operations are the following: integration and differentiation. So, let us consider first how integration is done or differentiation is done. Basically, operational amplifier is going to be primarily used to convert voltage to current. What is done is integration or differentiation can be done by using a capacitor or an inductor. We know that if you use a capacitor and an current I flows through it, through a capacitor of C, the voltage across the capacitor V is nothing but 1 over C integral I dt. That is, this is the charge that divided by capacitor is the voltage across the capacitor. So, this is the basic principle that is used in integration. In fact, you can use this the other way about, C dV by dt is equal to I. So, it can be used either as an integrator or as a differentiator. The same capacitor can be used. How do we do it? Here I want a voltage as an integral of another voltage. So, I merely pump into the capacitor a current which is proportional to voltage. So, this facilitates, this op amp here facilitates pumping in current, because there is a feedback here. This is going to be virtual ground and the current pumped in is V I by R. So, I through the capacitor is nothing but V I by R. So, what happens to the voltage across the capacitor V c is 1 over C integral I through the capacitor, which is V I by R dt. So, this is nothing but 1 over C R integral V I dt. So, I have achieved integration of a voltage, and what is V naught? V naught is nothing but minus V c. So, this is minus 1 over C R integral V I dt. This is an important function, linear function, which is useful for a variety of applications in analog signal processing, integration. How do we do differentiation? That is very simple. Once again, we have I equal to C dV by dt. That means, I have to establish a current which is proportional to an input voltage, let us say. So, I apply the voltage directly across the capacitor. So, V I is applied. So, the current through the capacitor is, this is C dV I by dt according to this. This is the current through the capacitor, and the same current is forced to flow through this resistance R and develop a voltage here, which is V naught, which is minus this I times, okay, this is I, this is minus R C dV I by dt. So, straight away by interchanging the resistor and the capacitor in this configuration, which is inverting, I can achieve integration as well as differentiation. Now, what does it really mean in terms of transfer function? This also can be done. Okay. We can replace this instead of the time analysis by the frequency analysis here. So, the impedance of this is 1 over S C, and therefore, the same thing is valid here. We have V I now, the RMS value of the input voltage, and the current is V I by R. Okay, that remains the same. The voltage here therefore, is going to be V I by R minus V I by R into 1 over S C. So, the transfer function V naught over V I is minus 1 over S E R. 1 over S means integration. Similarly, it can be shown that dVi by dt means yes, differentiation. So, this is equal to V naught over V I equal to minus S C R. Again, we can replace this by V I, this by 1 over S C, and the current is going to be S C into V I, that is the current through this capacitor, and the potential here is going to be S C V I into R with a negative sign. So, S C R V I. So, these are the transfer functions of these two blocks, which are very important linear building blocks. What happens? Let us understand. For DC, that is, put S is equal to j omega and consider for DC. Omega equal to 0, the gain is infinity. So, for an integrator, if you apply a DC, the gain is infinity, and therefore, ultimately output will go to saturation. Even if there is a small value of DC voltage here, right, it will keep on integrating and output will go to saturation. So, this is something that you have to bear in mind. This integrator, even if without any input, may go to saturation simply because of the offset voltages, which are of the order of millivolts, which are already there in practice in the input of an operational amplifier. So, basically giving an input DC here has this problem with this integrator, that it invariably lands up in saturation. Whereas in the case of a differentiator, there is no such problem. There is negative feedback as far as DC is concerned, and the gain for DC is 0 because the capacitor is decoupling the DC. So, gain for DC is 0, and as far as this operation is concerned, this is grounded. So, this is at 0 volts and output voltage will be stably at 0 volts. So, that is the advantage of biasing of the op amp in the case of differentiator as against that of integrator, because there is no DC feedback, negative feedback because of the capacitor, and therefore, bias stabilization is very difficult to achieve. The offset, input offset is going to make the output go to saturation. So, we can also see what happens when I apply a sine wave here. You can see that there is a phase shift of 90 degrees. Because of J, there is a phase shift of 90 degrees between the output and the input. So, this is the case with differentiator also. There is a phase shift of 90 degrees. So, both these blocks can be used to obtain an output which is in quadrature with the input. Phase shift of 90 degrees means output is in quadrature with input. That means, if input is A sin omega t, output will be B cos omega t. So, this quadrature component can be obtained easily by using integrators. Next, integrator is something whose gain is inversely proportional to frequency. That means, at high frequency it eliminates all the signals, whereas differentiator is something that will amplify all high frequency components. That means, a differentiator will respond even to noise which is occurring at high frequency. That means, if there is a voltage induced because of somebody starting a scooter or car or anything, that will disturb this differentiator, because that will appear at the input as an induced voltage, and that will be amplified considerably by the differentiator. So, normally differentiators like this are not used because they are amenable to noise. They are disturbed by, the output is disturbed by sudden fluctuation of voltage which can be picked up, and that will be amplified at the output considerably. Whereas integrators do not have that property, because they will suppress the noise at high frequencies. So, if it is just quadrature component you want, you would rather use an integrator than a differentiator. But the trouble with the integrator is, as such, because of no DC negative feedback, output is liable to drift and go to saturation. So, you might have to really provide DC negative feedback in order to stabilize output. We will see this later, how integrators can still be used with overall DC feedback so as to stabilize the DC at 0. So, consider example 7, which is to design a summing amplifier using only one op amp to give an output V naught equal to 0.1 Vi1 minus 0.7 Vi2 plus 100 Vi3 minus 10 Vi4. These have been arbitrarily chosen. So, as to facilitate design of any generalized summing amplifier, coefficients can be less than 1 or greater than 1, can be positive or negative. Okay. So, how to now approach this problem of designing using only one op amp a generalized summing amplifier, so that the design is quickly over. Now, let us concentrate on this op amp now. We are giving negative feedback here, and as I told you, with negative coefficients like in this case minus 0.7 and minus 10, can be easily got by designing an inverting amplifier. So, Vi2 and Vi4 which have negative coefficients can be fed to the op amp through resistors which will come to this point. So, that these inputs irrespective of the inputs connected to positive, when these inputs are not considered, this can be connected to ground. So, this will be ground potential and this will be virtual ground we said, and therefore, all these currents are going to get added. So, Vi1 divided by R by alpha 2 which is Vi1 Vi2 into alpha 2 divided by R multiplied by R. So, basically you get minus Vi2 here, which is this resistance divided by this resistance is the gain with the inversion sign. So, R divided by R by alpha 2. So, the coefficient is neatly chosen as alpha 2. So, alpha 2 in this case happens to be let us say 0.7. So, alpha 2 therefore is 0.7 easily identified. So, this is over. Then it will also sum up this Vi4 divided by R by alpha 4 which is Vi4 into alpha 4 okay, divided by R multiplied by R develops a potential which is minus alpha 4 Vi4, that we know this divided by this resistance is the gain with an inversion sign alpha 4. So, alpha 4 is going to be equal to according to our requirement is 10. So, very simple design. So, we have chosen alpha 4 as 10. So, if this is 1 k, this is going to be 10 k, this is going to be 0.7 k, that is sorry, this is going to be, if this is 1 k, this is going to be 100 ohms because R by alpha 4 100 ohms, this is going to be 1 k by 0.7. Therefore, we have easily chosen these coefficients in this manner. Now, coming to this. So, this is also finished. What happens now? Two inputs which are connected here, these inputs will be amplified without any phase shift or they do not have any change of sign. These are fed to the non-inverting terminal. So, from here to here there is a gain. You assume that these are grounded here now because we already considered what the output is due to this. So, these are not going to be disturbed. In addition, we will have an output due to this which is coming here. The voltage that is coming here because of this Vi1 and Vi3 which both have positive coefficients Vi1 and Vi3. This has 0.1, this has 100. Okay. This voltage is appearing here. So, in order to adjust the coefficients, I am putting some resistances through this. This is R by beta 1, this is R by beta 2. Suppose I put this, then what is the resultant voltage here? This will be from here to here, it will act as a non-inverting amplifier because you have two resistances coming in parallel here, okay, and there is a resistance in the feedback. So, this is your effective R1, this is your R2, that means gain is 1 plus R2 over R1, okay, which will be 1 plus alpha 1 plus alpha 2. So, the gain from here to here is going to be this 1 plus alpha 1 plus alpha 2. Why? If this whole combination is R1 and this is R2, R2 equal to R, the gain we have known is 1 plus R2 over R1. That means 1 plus R. R1 is parallel combination of this which is alpha 2 over R plus alpha 4 over R. So, essentially you will get the gain as 1 plus alpha 1 plus alpha 2. Okay. Alpha 4, sorry, alpha 4. Okay. Then the attenuation because of this is beta 1 divided by beta 1 plus beta 2. Actually speaking, it will be this resistance divided by this plus this for this resistance divided by this plus this. Okay. So, for example, for Vi1 it will be R by beta 2 divided by R by beta 1 plus R by beta 2, which is really beta 1 divided by beta 1 plus beta 2 times Vi1. That is what beta 1 by beta 1 plus beta 2. The other one is beta 2 by beta 1 plus beta 2. Easy way to remember is, if this is a conductance which is beta 1 into G, if this is a conductance which is beta 2 into G, it is that conductance which is connected to that voltage divided by sum of all conductances. Right. So, beta 1 G divided by beta 1 G plus beta 2 G. This voltage is beta 2 G divided by beta 2 G plus beta 1 G, that is all. So, that is the output. And if I make beta 1 plus beta 2 equals 1 plus alpha 1 plus alpha 2, this I have to see. Then I can conveniently select beta 1 as, because Vi1 coefficient which is 0.1 and beta 2 as Vi3 coefficient which is 100. Right. So, this kind of design can I do? I have to have now beta 1 plus beta 2 equals 1 plus alpha 1 plus alpha 2. Therefore, I can cancel this. How do I do this? Now, let us see in our design. 1 plus alpha 2 plus alpha 4 is this 10, 11 equal to 11.7. That is 1 plus alpha 2 plus alpha 4. Beta 1 plus beta 2 is going to be how much? Beta 1 plus beta 2. This is 1 plus alpha 1 plus alpha 4. This is equal to 0.1 plus 100. 100.1, which is greater? This is greater. Beta 1 plus beta 2 is greater than 1 plus alpha 1 plus alpha 4 by an extent which is, let us see. That is all, 88.4. How do I give this? How do I therefore satisfy this? So, I have to introduce something along with this, so that this will be, let us say, some alpha 0 which is 88.4, then this condition will be satisfied. So, I have to introduce here an alpha 0, okay, which is 88.4, then this condition is satisfied. So, but that alpha 0 should not be connected to any input voltage, because it should not contribute to any output. So, I simply put a resistance here with R, the input to this is 0, dummy resistance. So, that this generates an alpha which is R by alpha 0, and alpha 0 is equal to 88.4. Now, this will have 1 plus alpha 0, and we have purposely selected alpha 0, so that beta 1 plus beta 2 is equal to 1 plus alpha 1 plus alpha 4 plus alpha 0. That get cancelled here, and we get this design in a very simple manner, representing straight away. Answer is very simple. Alpha 2 is corresponding to 0.7, alpha 4 corresponds to 10, beta 1 corresponds to 0.1, beta 2 corresponds to 100. Then I have to make only alpha 0, okay, adjustment, so that my design becomes very simple. So, whether I use here any number which is greater than 1 or less than 1, positive or negative, these designs will remain very simple in terms of these alphas and betas. So, this is the technique of designing it. Now, one word of caution, it may not be that the resistance, dummy resistance always comes here to ground. when for example, here okay, 1 plus alpha 1 plus alpha 4, if it is greater than beta 1 plus beta 2, you might have to put a resistance here to ground. Okay. So, it is either this to ground or this to ground, that depends upon the relative magnitude of alphas plus 1 with betas added together. So, this is a very intelligent design actually, so that the designer looking at the problem can straight away write down the answer without much of an exertion on his part. Historically, operational amplifiers have been used in what are called as analog computers in simulation of differential equations. Therefore, let us see how the present day op amps also can be used for that purpose. The op amps are available as cheap components, and therefore, it is very easy to simulate these equations using such operational amplifiers. Therefore, the variable I am taking here is voltage. So, d squared V naught by dt squared plus some alpha d V naught by dt plus gamma V naught is equal to V I is a second order linear differential equation. Second order, this is the order, right, second order linear differential equation. I want to simulate. What you do is d squared V naught by dt squared equals from this equation V I minus alpha dV naught by dt minus gamma V naught. The same equation is rewritten this way. So, what we start with is, let us assume that d squared V naught by dt squared is somehow available to us. Suppose d squared V naught by dt squared is available to you. How will you obtain dV naught by dt? You will integrate it once. So, I put an integrator here. This is say R C. So, output is going to be minus 1 over R C, that is what we have seen earlier, integral of d squared V naught by dt squared, which is dV naught by dt. So, you got dV naught by dt by integrating d squared V naught by dt squared. Now, using this, if I once again integrate, I can get V naught. So, I put another integrator. So, at the output of this is going to be integrated again plus 1 over R squared C squared, because this R C comes into picture, integration of dV naught by dt, and sign becomes plus. So, this is V naught. So, I have got V naught with some constant factor, dV naught by dt with some constant factor and a negative sign. So, these two things are created by me, assuming that d squared V naught by dt squared is available. V I can be happily added. V I is an independent input. So, V I is available, this is available, this is available. How do you get therefore summation of all these things? Let us see. V I should be added without any, let us say, inversion or anything. Fine. V I is to be connected to the non-inverting terminal, because coefficient of V I is positive. Let us see another thing. As far as this dV naught by dt is concerned, already there is a negative sign, and that has to come as such without any change of sign. That means, this also should be connected to the non-inverting terminal. Okay. So, what I do is I put here alpha R and 1 minus alpha r. So, what happens here? This output will come as alpha times, okay, let us call it alpha zeros in order to distinguish, alpha 0 times this value, okay, of it will come here, alpha 0 times minus 1 over R C dV naught by dt will come here because of this attenuator, and what other portion of V I will come here, plus V I into 1 minus alpha naught. By putting this attenuator, I have got this part as well as this part with some other coefficients here. We can change the coefficient by again using some other multiplying factor while adding, and then this V naught by R square C square is positive, but I want a negative thing. So, this has to be applied to the inverting terminal of the summing amplifier. This we have already discussed earlier, how to design the summing amplifier. So, I can now change the sign here by using, let us say, R and R. So, output will come as minus V naught by R square C square. So, this is already coming as minus V naught by R square C square. With this introduction here, this will come here and this can be connected to this. So, what happens here? Already this has been summed here. From here to here, there is a gain of 1 plus R by R, that is 2. So, these will appear at this point as 2 into 1 minus alpha naught, okay, into V I minus alpha naught into 2 by R C into d V naught by d t. So, you can see here that essentially I have got the right hand column on this side, okay, with the proper sign, except that these coefficients have to be properly selected in order to make whatever they are. This may be made equal to 1 and this is 2 alpha naught by R C is made equal to alpha and gamma is equal to 1 over R squared C squared, like that you can select. So, this is now to be made equal to d squared V naught by dt squared. That can be done because our equation says this is in fact d squared V naught by dt squared. So, I connect this here. So, this circuit therefore simulates this equation. Connecting this here means I am making the right hand side, which is this, equal to the left hand side, which is this, what I have assumed. Okay. So, this in fact simulates a second order differential equation, and this circuit is called KHN network. It is Kelvin Hulsman Newcomb, okay, KHN network, or also called universal active filter, abbreviated as UAF. This whole thing is available as an integrated circuit. Okay. Therefore, we are now first introduced to simulation of the second order linear differential equation. We can come up with fairly arbitrary coefficients for this and simulate any second order differential equation, okay, with alpha and gamma being always positive. Right. That is, so as to have only stable solutions for the differential equation, we are restricting alpha and gamma to be always positive. Such a case, right, this differential equation will give a stable solution transient or steady state. And the input, when it is sinusoid, we can find out what the output is. Output in this differential equation, if input is sinusoid, output is also going to be sinusoid. This sinusoidal analysis we can presently do independently and see for this circuit what are the respective transfer functions from this output to this input, this output to this input, and this output is this. Okay. What we just did was to start with a second order differential equation and come up with a circuit which can simulate that second order differential equation. Now, we are going to analyze it using for the analysis the sinusoidal response. So, for that the same circuit is redrawn. We will consider this as V naught 1, this as V naught 2, this as V naught 3. Now, V naught 1 is here, it is integrated. So, minus V naught 1 by S C 1 R 1 is the transfer function here, minus 1 over S C 1 R 1 integration. Again it is integrated once again. So, plus V naught 1 by S squared C 1 C 2 R 1 R 2, second time integration. This is already minus V naught 1 S C 1 R 1, this is V I. So, what will be the V naught 1 therefore? Let us see, this minus V naught 1 will come here as alpha times, that just as we did in the earlier equation, okay, times minus V naught 1 by S C 1 R 1 plus 1 minus alpha times, right, V I, and that gets multiplied by a factor of 2. So, you get 2 into 1 minus alpha times V I, okay, minus 2 alpha by S C 1 R 1 V naught 1, and from here it just simply gets inverted, this can be grounded. So, minus V naught 1 by S squared C 1 C 2 R 1 R 2, and that should be equal to V naught 1. This is the same thing as d squared y by dt squared being equated to something of dy by dt, something of y and something of input. So, V naught 1 into 1 plus 2 alpha by S C 1 R 1 plus 1 by S squared C 1 C 2 R 1 R 2. This is equal to 2 into 1 minus alpha times V I, or V naught 1 over V I, which is called the transfer function at this time, V naught 1 over V I is equal to 2 into 1 minus alpha divided by, okay, S squared C 1 C 2 R 1 R 2, okay, plus 2 alpha S C 2 R 2 plus 1 into S squared C 1 C 2 R 1 R 2. From the equation here, this is what we get. This transfer function with S squared here and S squared into something plus S into something plus 1, this is called high pass filter transfer function. You can see that at very high frequencies this S squared dominates, the output will be 2 into 1 minus alpha. At very low frequencies, S equal to j omega, put omega equal to 0, this is going to be 0. So, the output is going to be 0 at 0 frequency, goes to ultimately 2 into 1 minus alpha at high frequency. So, it is called high pass filter. The output is going to be like this, going to 2 into 1 minus alpha at omega equal to infinity. Right. This is therefore high pass output. If you integrate this, the output here is going to be same 2 into 1 minus alpha with a negative sign, because you are going to divide by S C1 R1 and there is a sign change. So, you get S C2 R2 divided by the same denominator. So, S squared, okay, C1 C2 R1 R2 plus 2 alpha S C2 R2 plus 1. This is actually 0 when S is equal to j omega, omega equal to 0, and 0 because of S squared at S is equal to infinity. So, this is called band pass filter transfer function. 0 at S is equal to j omega, omega equal to 0, 0 at S is equal to infinity, omega equal to infinity, and you will see that it is going to be maximum when omega naught squared is equal to 1 over C1 C2 R1 R2, because this will get cancelled with this. S squared becomes minus omega squared. So, 1 minus omega squared C1 C2 R1 R2 becomes equal to 0, and this will become the highest, which is minus 2 into 1 minus alpha by 2 alpha. So, this depends upon 2 alpha. If alpha is very small, this goes to a peak. This is called resonant frequency. Okay. So, it becomes a peak at omega naught squared equal to 1 over C1 C2 R1 R2. That is the band pass transfer function. Once again you integrate, you will get this output here as again this sign changes to plus divided by the same denominator, and therefore, that is called low pass, because S is equal to 0, it is 2 into 1 minus alpha, S is equal to infinity, it is 0. So, it is low pass, that is going to be constant at 2 into 1 minus alpha, and then we therefore go down to 0 as frequency increases. The band pass is going to look like this. So, these three outputs are simultaneously available in this case, and that is why this is called universal active filter. You can get low pass here, high pass here, and band pass here. A combination of this low pass, high pass, and band pass can be got by using additional summing amplifier, and therefore, you can generate any second order system using this simple block. And these are called poles of the system, these are called zeros. The poles of this system lie always on the negative real axis. So, the system is always going to be stable, and this is a very stable filter function. Okay. And this is universally used, that is why it is called universal active filter. The whole block with additional summing amplifier is available as an integrated circuit for synthesizing any transfer function, second order transfer function, using this block. You can use successively these blocks to generate any higher order filter function. By cascading such filter blocks with one first order block, you are capable of getting any higher order filter block, and therefore, this is studied thoroughly so as to facilitate synthesis of any higher order filter block.